Welcome to the Air-Sea Fluxes from Space webinar series. Today we have Owen O'Driscoll, who is a PhD student in Delft. And he's going to talk about work that he's done with Alexis Mouche, Bertrand Chaperon, Marcel Kleinherrenbrink, and Paco Lopez-Decker, working both at Ifremer and Delft on air-sea fluxes from kilometer scale SAR observations. So take it away, Owen.
Thank you very much, and thank you for hosting me. So yeah, I'll be presenting about this project done in collaboration with Ifremer and TU Delft. The objective of this project was to try and quantify the type and the air-sea interactions occurring at the air-sea interface using the textures which we see in SAR imagery. So I have here two SAR images. One has a bit of a bubbly texture, whereas the other one is more streaky, aligned in a certain orientation. And from these texture differences, we would like to quantify what type of air-sea interaction is occurring and induce or find out what the fluxes are associated with this with these interactions. So at risk of repeating what everyone here knows, I'd like to briefly mention that the radar is sensitive to roughness on the scale of the same wavelength of the radio wave, which is approximately a centimeter scale. So if we have the ocean surface with the larger waves, it is the smaller waves which are the dominant source of reflection back to our observing tool, our SAR system. And the main mechanism there is something called Bragg scattering or resonance scattering, where if we have all these small scale waves, these capillary waves, fortuitously spaced, we get an increased signal back. So anything oceanographic or atmospheric that influences these very small waves is something that we can observe in our radar images. So if we would then consider what type of atmospheric phenomena would produce such a radar scene, such a texture, well, I have a cross-section here on the right where we have these convective plumes, and locally where we have downdraft of these convective plumes, where the downdraft hits the ocean surface, it amplifies the ocean surface roughness, creating more of these small-scale waves. And then where we have, conversely on the other side of the cell, also downdraft, but this cancels out with the vector from our mean surface wind, so that we get patches of enhanced roughness, enhanced brightness, and decreased roughness and brightness. We can see that in our image where we have locally a bright patch and a dark patch. So this image is indicative of a particular type of atmospheric state in which we have these convective plumes in our boundary layer. If we go to the next image, which is more streaky, it is a similar mechanism, but now instead of plumes, we have these streaks or rolls where the downdraft in a roll-like structure locally enhances the roughness, the brightness, creating a streak of bright, and then half a wavelength away, we have a streak of dark. So we get this streaky, bright, dark pattern. So this is to show that the atmosphere or the wind field of our atmosphere can imprint itself onto the ocean surface and modulate the small scale waves, which we can see with our radar. So then if we would want to try and quantify what type of atmospheric state we have, we could look at a surface layer stability metric, such as Obukhov length, which is like a ratio between horizontal production or shear production of a turbulence and convection production of turbulence. So if we know that in the left scene, we have these convective plumes, this is probably very unstable because we have more vertical convective component, a stronger component. Whereas in the scene on the right, we have more shear, it's more shear driven, So the numerator is greater, meaning that we have a greater negative Obukov length, so it's less unstable. So this is nice because then we can kind of classify it, but we want to do so more quantitatively. So instead of saying it is unstable or very unstable, we would like to pinpoint either the Obukov length value or another value associated with the textures. To do so, we start from a pre-classified selection of sarsenes. And this is, so we use about 250,000 sarsenes, where half are convective streaks and the other half are convective cells, are the cellular patterns. So those are class B and C respectively of this classification done by a former researcher at Ifremer Chen Wang. And he also has classes showing or detecting icebergs here on the left. I think these are ocean slicks and atmospheric and oceanographic fronts. So we rely on the two subclasses of his classification. Then for each of these scenes, the arrow here is a bit off, but we, per pixel, calculate the associated wind speed. So we convert our backscatter to an associated wind speed. This is certainly wrong and will introduce errors, as we're relying on empirical models called geophysical model functions, which are designed for a far coarser resolution. So to do this conversion basically on a 20 by 20 kilometer scale, whereas here we're doing it on a 100 meter by 100 meter scale. But I believe it doesn't matter for the purpose, but we can get into that later. And then for each of our wind fields, we want to estimate some atmospheric parameters. And for that, we have validation using collocated ERA5. And for a smaller subsample, we also have buoys, but I don't show those here. Here I have two examples of wind fields. And I would like to point out that according to ERA5 and our own estimates of the average or median wind speed, which is the first two values here, they're approximately the same. So it's hovering around 6 meters per second. But the texture we see is very different. So the one on the right is clearly more bubbly, whereas the one on the left has these streaky patterns. If we ignore the high frequency swell, which is superimposed on the streakiness. So this is to show that even if we have the same wind speed, we do not, or that alone is not enough information to discern the stability state. So using first order moments is insufficient. But inspired by work which was done almost 25 years ago, we can calculate from our wind fields a synthetic turbulence spectrum, or assuming our wind field is correct, we would call it a turbulence spectrum, which is inspired by more atmospheric sciences. And then the amplitude of this turbulence spectrum, if it follows a particular slope, we can relate to the degree of turbulence occurring in our wind field. So if we have a higher amplitude, we would say we have a greater amount of turbulence, so more convection, and vice versa. So if we normalize this slope with frequency and turn it into a single value, we can plot that against what we get from ERA5 from our validation, which is shown here on the left. So if we have a higher normalized amplitude, which is on our y-axis, we expect more unstable scenes. So we have more unstable scenes. And if we have a lower amplitude, so we have less turbulence, then we expect to be less unstable, so more streaky. And that is kind of what we see in this trend here, a bit of a trend. And I can pull up the two examples I showed before, where this scene, if we again ignore the swell and have a bit of the streaky patterns, it is less unstable because it has less variance, lower amplitude, whereas the scene B has a greater convection, has more amplitude in the spectral domain. But as you might notice, the standard deviation here is quite large, and there's a bit of a bifurcation occurring here at a particular range of Obukov lengths. So we cannot give an unambiguous estimate of the Obukov length using this approach, relying only on the spectrum. So the point is, from our spectrum, we can clearly get some information about the RC interactions, but not enough. So instead of relying only on one parameter from our 1D spectrum, we remain in the 2D spectrum and extract a whole bunch of spectral parameters, which we believe are important to the phenomena of our wind field, so of our atmosphere. So for instance, we know the approximate size of the rolls and the cells. So we constrain the parameters which we extract to be of the same size. And then we consider the orientation and the distribution across the angles, et cetera, So we end up with a whole bunch of spectral parameters for each of our wind fields. And then using all these parameters, we would like to give an estimate of Obukov length or Richardson number or heat flux or something. But now we don't have the analytical framework to rely on, which George Young created 2 decades ago. So instead, we're relying on machine learning, where we have 5 different machine learning models, regression models. The top 3 are the state-of-the-art gradient boosted models, kind of like tree-based regression. And then the bottom 2 are linear regression models with different regularization parameters. Each of these models is trained on the training part of our data, giving us a model capable of predicting whatever parameter we're trying to regress towards. So we get 5 separate predictions for each scene. And then we have a second layer, a stacking regressor, which is usually a simple linear regressor, which is able to select, based on the outputs of the previous regressions, what is probably the best regressor. So the stacking operation basically chooses the best of all these individual components, which is so the output of the stacking regressor tends to outperform any previous individual one, which is quite nice. So then if I go over to the results, where I've confusingly plotted our estimates on the y-axis and the validation on the x-axis, we can see that the histogram of our estimated Obukov lengths is approximately the same as the histogram of the Obukov lengths we see in our validation data set, where we are somewhat nicely along the center line, except for where we have fewer data points. And using this architecture where we train regression models on spectral parameters, we're able to explain approximately 80% of the variance with respect to our validation, with a median relative error of about 30%. So if the true value of Obukov length is minus 100, 50% of our estimates would be between approximately minus 130 or minus 70 meters. And this is for Obukov length, but we get similar performance when we are regressing towards latent or sensible heat fluxes or buoyant fluxes, presumably if we would train towards Richardson number, because I believe these are all related. And we get a bit lesser performance when we are training towards the temperature difference of the atmosphere and the ocean. So then we're only able to explain 60+% of the variance, presumably because what we are observing is not only forced by the temperature difference, but there are extra components. Now, results always look better on a map. So I have here a 2-year average, 2-year median on a, I believe, 3x3 degree spacing of our validation of Obukov length versus our estimates, and a map of the difference, where in the polar seas we have fewer data points, so the difference is generally greater. But between about 30 degrees north and south, we have quite a lot of data points, and we see a lot of bright white areas where the difference is rather small. Although there are some regions where we have correlations in the errors, in the sign of the errors. For instance, here south of the Bay of Bengal, we have a region. West of Namibia, Cabo Verde, we have another region, and here we have a flipping of the sign. So there are some regions where, despite having a lot of data points, we are unable to regress towards our reference data, which could be indicative that the information we extract from our radar image is insufficient to explain the phenomena that are occurring here. So maybe we have too few degrees of freedom, or perhaps the reference data itself is suffering from some sort of an anomaly. This is the result I showed before, which was achieved using all our spectral information. But we can also train models using only wind speed and viewing geometry. So that would be the result obtained from a synthetic scatterometer where we don't have access to the high resolution information. And we see that the achievable R-squared metric here is quite similar. It only drops about 9% points, which might make us conclude that the kilometer scale information is redundant. So we don't necessarily need star systems to achieve this. But in fact, the main benefit of using this high resolution information is in reducing these median errors. So if we don't have access to high resolution information, the median errors go up proportionally more than the drop in explained variance. And I can show that with our two example scenes, where if we have similar wind speeds and we only rely on wind speed and viewing geometry to make our estimate, if they are the same, our model does not have enough degrees of freedom to explain the observed difference. So in this case, if we have a lot of parameters from our SAR, all this high resolution information, we are able to approximate the Obuchov length from error 5. Whereas if we only rely on information from a scatterometer, we perform a lot less at approximating the atmospheric state. So we need this high resolution information to make a real case-by-case estimate. Otherwise, we're just training towards like a global average. Since our SAR model, so the one trained with all our high-resolution information, outperforms the scatterometer, and we can assess the difference between the outputs of these two models. And this will basically give us a map of where high-resolution information is most necessary, where it's necessary in order to make a good estimate. And that is the map shown here. So we can see that for regions with complex mechanisms driving convection or forcing the convection or interactions, such as over the Gulf Stream or the currents of the coast of Japan, then we need more degrees of freedom to explain what is occurring. So basically, this is a map telling us where we are deviating from the global mean. So to conclude, from the textures in our SAR images, we can derive quite some parameters related to the air-sea interaction. And we can quantify, for instance, Obuchov length or the heat fluxes. In order to do so, we need this kilometer scale information, because otherwise we are training towards a global average. I don't list it here, but also in results, we see that we are quite dependent on the viewing geometry of our system. So if we would have a system with greater number of viewing geometries, that would be beneficial because of how the SAR image observes the ocean surface. And lastly, in the errors of our estimates compared to our reference data, we see regional correlations, which could be indicative and be used to diagnose shortcomings in our reference data, assuming that our estimates based on these real measurements are correct. Then I've listed some possible next steps, such as to perform this analysis on larger scenes. So the analysis I showed here was on these smaller 20 by 20 kilometer scenes. But if we would instead apply it on wide swath scenes, such as one shown here, we could really trace the texture transitions and relate those to the transition of the interaction between the ocean and the atmosphere. Also nice to mention is that we had a student try and work out some physical features and relate their importance to the atmospheric interactions. So instead of relying on some abstract spectral parameters, she was looking in particular at one physical feature and seeing how important it was. She had quite some success. And there are some other things. Maybe lastly, I'll mention that in this conversion from our backscatter to our wind field, this empirical formulation assumes a particular atmospheric state, a particular atmospheric stability. In fact, it assumes a neutral stability. So if we have an estimate here of the non-neutrality of how unstable our scene is, we could perhaps use that to improve these inversion schemes so that from the texture of our radar scene, we not only get the backscatter for only neutral conditions, but also based on our estimate of the real conditions. I'll leave it at that. Thank you very much. And I hope this was informative.
Thank you. This was great. Questions for Owen? And maybe while people are thinking of questions, I'll ask about, you showed an example with really nicely distinguished speckly patterns versus elongated patterns. How hard does this get? I guess the ocean must have moments when there are intermediate states. How does it get harder to do this in intermediate states? Are you?
Yes, that's a good question, because we don't only have these neat two classes. I think well, I know of some work that's being done now to like find the classes, the transition classes between those. And in fact, we can kind of already see it, I think, in this scene where we have a transition of the more cellular structures into a more elongated. But I don't think it matters per se, because it should occur along a gradient. I don't think there's a sharp cutoff. And we can also see that in the results, if I go back, where there isn't a surprising dip here, despite this including both roles and cells, because I think it makes more sense to view it really as a regression problem than as these distinct classes. We do have to do some aggressive filtering beforehand to remove scenes which have clearly no convective signatures in them, because we are relying on, what is it, 250,000 scenes. There is bound to be some scenes in there which are not as neat as intended. And in fact, we're using the work from George Young here to find what sort of features are related to turbulence, and then basically filtering out the rest. So yes, we rely on the transition. We don't think it's a sharp cutoff, but we do some filtering.
Thanks. I see there's some hands up. Claudia Pescaro can go.
Thanks a lot. Very nice, Owen. You mentioned that you repeated the SAR exercise also with scatterometer data, and I'm not sure I fully understand what you meant also, because you use the word we rely on the global mean. So was the exercise exactly the same? Did you use the same spectral parameters that you used for SAR in that case? No, wind speed and viewing geometry only. So you use only those two things, but on a completely different scale, right? Spatial scale.
So we basically rely on one wind speed, like the average wind speed of our scene, and then we have our like the orientation of that wind speed with respect to the radar sensor, and then the incidence angle of the, in this case, the radar sensor. Those are the three parameters which we say are equal to our synthetic scatterometer.
So you don't use the actual scatterometer data, but you
No.
extracted those the information that you would get from scatterometer, but you extract them from SAR essentially.
Yes, so we are
Okay.
basically blindfolding
Yeah.
another model and withholding all this high resolution information.
Okay, thank you very much.
You're welcome. Thank you.
And then Momihel has his hand up.
Yeah.
Let me go
Hello,
ahead.
very nice talk. I wonder, so you decided to go in spectral space because there's this nice theory from Young, and then you left, then you made it more complex by estimating all these different spectral parameters. Since you're leaving the strict theory, did you think of leaving the spectral space as well? Because you're assuming things are homogeneous and Gaussian distributed, but you could also just look at the distribution of the data, and there's probably some information in there as well.
Yes, that's a good question. And there's probably other parameters which we can derive not from the spectrum, so for which we would need phase, for instance, which could be more informative. We chose not to, because the narrative we're going for here is that we can achieve that all using these second order moments, which is perhaps an easy way out of your question, but yeah, that's the case. So I think if I would try and bump up this number even more, I would include information which beyond just the spectrum.
Okay, thanks.
There's a question in the chat from Ralph Foster, who asks, when you convert SAR resolution NRCS to U10 via GMF, what do you use for fine scale wind direction? Ralph, I don't know if you want to flesh that out at all.
Yes. So when we have to do our conversion, this conversion from our backscatter, this empirical relation requires a wind direction. Either you could estimate that wind direction from the scene itself. For instance, if we have streaks, we know that the streaks tend to be aligned with the wind direction, so we kind of have an estimate there, but not so much for cells. So for consistency's sake, we rely on the wind direction from era 5, which again introduces an error here, which I guess is you're hinting at in your question by referring to fine scale wind direction. Because of course, if we have these cells, if I go back to the schematic, we have different wind directions occurring at different locations in our image. And this is not taken into account in this conversion. So there again, our conversion is making errors. I think this is not necessarily an issue, because if I see the calculation which this GMF is doing, I see it more as affecting a particular range of frequencies in the frequency domain, which are not necessarily the frequencies I'm interested in. I believe this is more on the either the very high frequencies or the very low frequencies, and we're interested in these in a scale range of hundreds of meters to kilometers. So although it is wrong to use a GMF in this case, it will introduce errors. I think for the purposes, we don't have to consider the fine scale wind direction.
Ralph, does that answer your
I
question?
don't see any aggressive typing. So.
Well, if I can move on in the questions, I guess I wondered, you're working with existing SAR, but there is the plan to launch Harmony, which will provide multiple views. And there are other ideas that have been proposed to have a SAR system that would get multiple looks at the same patch of ocean. What would an improved system do?
I think the added observations from different viewing geometries could be beneficial here. We know, for instance, looking at this data set, that some classes are more often observed during a particular incidence angle, or if it's orientated with the wind speed, either at the satellite or away. So our viewing geometry clearly biases what we see in the radar imagery. And in fact, I believe you can have a scene where if it's seen from two different positions, one might see cells and one might see rolls, even though physically we just have a mix of the two. So if we would have more degrees of freedom from a viewing geometry point of view, I think that could be beneficial. And even if, for instance, for Harmony, the added viewing geometry is not 45 degrees, but it's less, so we wouldn't be able to view it from the ideal angles, but perhaps again using a similar framework, these regression models, we could still learn and interpret how the behavior changes for a wider range of viewing geometries. So I hope to I think these added viewing geometries would definitely be beneficial. I see also that another question has popped up.
So Ralph put some extra comments in the chat. The risk is that you mix different components of the turbulent spectra. Along is greater than across usually. I think this gets to the difficulty in beating down the inherent error in estimating stratification. So I'm not sure if Ralph is in a position to talk, but and if you want to fill that in, Ralph. Roger Samuelson has his hand up, so maybe we'll move on to Roger.
You showed some maps of the accuracy of the inversion. And I'm just wondering if you showed a map of say, the percentage of conditions under which would fall into these classes for which you can make estimates. Do you have a sense of what that map would look like? Because if I understand right, you can only make estimates in certain classes of ocean atmospheric conditions.
Yes, that is correct. So we are relying on these, basically we can make estimates for these two classes. There is a recent paper published by, I believe Ralph, who is in the chat now, and Doug van der Mark, where they're looking at the classes A, B, C. So that is no convection, no convective signature. Please correct me, Ralph, if I'm misrepresenting this paper. And then these two other convective classes. And what they see is that the distribution of those, they do like a global mapping of where they occur and how much of a particular class. They see that matches their distribution matches the distribution of in this case, they're looking at Richardson number, and the Richardson numbers associated with their three classes matches or fully captures the global distribution of Richardson numbers over the ocean. So that using just these three classes captures basically all the convective unstable atmospheres. So I think if that is the case, and we are relying on the class B and C, which really have the textures, then we should be sampling most of the radar images which actually contain signatures from convection, because a per definition does not have convective signatures. Does that answer your question?
I guess so. It means that it's the fraction of the system which is in unstable conditions, more or less. You capture pretty much all of that, but you don't get the stable ones.
Correct. Yeah. Yeah.
Okay, thanks.
Ralph says he has no microphone, but he says, I could see the imprint of our maps in your error fields.
The inference. Let's just go back to yeah, I believe I'm gonna get this mixed up now, but the cells are more or less constrained to one region, and then you have roles more often occurring in another, of course, with some overlap. But I believe this is a paper published this year from Ralph and Doug and co. I see you posted another question. Yeah.
But 20% globally are class A, and they are stably stratified. So I guess if I can ask one more question about hypotheticals, you said that scatterometry didn't have the resolution that you need to do this effectively, that you really need the SAR capabilities. Is there a potential that if you get even higher resolution, super high resolution SAR type system, that would make a significant improvement? Or do you think that the SAR capability is really hitting the sweet spot for this?
I think at a high resolution, the relative gain might be negligible because you run into issues with the SAR imaging process. So now these wave mode images have a theoretical ground range resolution of, I believe, 5 by 5 meters in range and azimuth. We resample all of them to about 100 by 100 meters. And perhaps we could resample them to an even coarser resolution, primarily because the textures we're interested in are in the hundreds of meters up to kilometers. So a higher resolution would not necessarily be beneficial, but also because of how the ocean behaves. The effective resolution is already 100 or 200, 300 meters. So making a system which can theoretically achieve a high resolution would not be beneficial, I think, unless you could somehow mitigate this SAR imaging issue and really get the ground range resolution of greater.
I think the other promise.
So yeah, I think SAR is.
Yeah, go ahead.
Sorry, that was it. Yeah.
I think the other possible capability from the sort of SAR system that Harmony will have with multiple looks is to maybe get winds as well as the surface structure. Is that right? Would that make a difference in terms of the fine scale wind that Ralph was alluding to?
I think that certainly, and also the infrared tools, the infrared imaging. So if we can, these are all variables which we could basically either aid in converting our backscatter image to a proper wind field, a more realistic wind field, or just variables which we can include in our regression. And so yeah, I think these would be informative.
Well, thank you. Are there any other questions? If not, I'll stop the recording and we'll wrap this up. Thank you very much for a really great talk.